Thank you, everyone, and thank you. This is the last presentation of this session, so I'll be just trying to make this as quick as possible. So, in this presentation, there have been some outstanding set of speakers here, and my objective in this presentation is to bring to you my personal experiences of what is missing in building a CXL device which can be implemented at scale in a warehouse class data center, right? And specifically, I'll try to shine a light on 3 issues. And I was indeed very fortunate when I was developing CXL devices to work with many of you in this room, customers, partners, and CPU providers. So some of this commentary is a little bit personal and born out of personal experience. So really, there have been very eloquent speakers today, very fortunate to be able to hear them out. And essentially, the memory tiering paradigm for me falls into 2 big buckets. The first one is app aware, and the other one is app transparent. And really, the interesting bucket for me as a component supplier into the ecosystem is really the app transparent, because that is the one that allows me to scale up the solution and not have to wait for the applications to change over a 10 to 15 year time period. I need to move the memory into CXL as fast as I possibly can. So in that respect, Alex Branover and just now Reddy talked about there are 3 paradigms here. The paradigms are guest OS managed, or hypervisor managed, or hardware managed. And of course, the most difficult among these is the hardware managed. That is where we become completely become completely app transparent. And as you move from the right of this figure to the left, the degree of software change that is required to enable memory tiering continues to increase to the point where the app ends up having very fine-grained control, as Reddy just showed very, very eloquently. There's one more point on the slide is, as excited as we are about CXL and the southbound standardization of this CXL between the CPU complex and the device, we at times forget the northbound interface that also needs to be standardized between the CPU complex and the software layer. And the 3 examples that I'll show you will demonstrate the need for also focusing on how the software works with the CPU complex and the device. And it is just not the CPU complex and the device, but it is actually the full stack problem, which has 3 very important components: the software layer, the CPU complex, and then the device. So in particular, I'd like to draw your attention to 3 aspects of the problem. And the first one is page migrations. The second one is quality of service orchestration in virtualized deployments. And the third one is security orchestration. In the software controlled page migrations, it's a very important concept. Many speakers have shown a light on it, especially in the case of capacity memory, as Chris spoke very eloquently. The page migration is a very important mechanism to be able to preserve the end user experience by optimizing the working sets in the various tiers of memory, right? And the page migration is a policy-based engine. As Reddy just said, you can have various policies, migration on first touch, migration on fifth touch, or there can be various other predicates. But really, there are 2 fundamental mechanisms that we know of today in page migration. The one is it can be hardware assisted with the control plane lying in software, or as Alex talked, it can be entirely orchestrated within the hardware by the CPU complex or with the CPU complex and the device. In either case, in the case of software controlled page migrations, we need some serious hardware assist. And there are at least 4 categories of hardware assist that come into play here. The first one is, as Reddy just said, we need to understand how the page table or TLB locking or how the TLB flushes happen, and we need to manage them as we are migrating pages. The second one is the page migrations can be 4 kilobyte to as much as 2 megabyte, and so we need to be able to intelligently deconstruct and prioritize this page migrations. The third one, which is kind of sort of, we struggled a lot with this, was the I/O DMA management, right? The pages are moving, there is RDMA network traffic coming on to these pages. It can have some serious consequences in the operation. And the fourth one, which we also struggled with a lot, is hot page detection or page temperature monitoring, because eventually, if you start thinking about bandwidth memory on CXL, tracking hot pages going to warm or cold is fundamentally important. It is not as important to track cold pages going to warm. Rob Sprinkle and other people have taught us that via their paper. But so this is a very important attribute. And while we were designing this out for embedded implementation, we lost a lot of cycles in trying to make it work correctly. A lot of cycles. And and then finally comes the kicker, which is that page migration. When you are developing as far memory, the capacity memory, the primary touch model to the memory becomes page migration. And if the primary touch model to the memory is page migration and not direct access, then at that point, the cost of page migration becomes a very important factor. So we started to worry about page migration efficiency and started to look at the various options for hardware offload of the page migration efficiency. And CPU memcopy is very popular, very easy to do. And as we started to work on it, we found that it works really well for cache line, low latency, synchronous access. But for page migration is not entirely suitable. And we started to figure out that we were actually burning a lot of CPU cycles in managing page migrations with memcopy, and it was a blocking operation. And with this blocking operation, we were starting to lose some of the benefits of this end-to-end customer experience. So what I'm really calling out here, you can read the slide, what I'm calling out here is that we really do need to think about a DMA offload engine over CXL.mem, which gives the flexibility to the software stack to be able to use memcopy as it is appropriate for direct accesses or for other cases, and is able to use a more bandwidth-oriented approach to be able to migrate pages between the various tiers. The second problem that we really struggled with was quality of service control for virtualized deployments. This is something that we got from customer feedback, and the customer really worked very, very closely with us and the CPU partners. And the key problem statement that all of you are very well aware of is that the container VM in multi-tenant deployments, it is quite possible that you could have a aggressor VM profiling the posture of your infrastructure and then mounting an attack to slow down or to deny service to the other VMs, and we must prevent that. And so we started to look at alternatives as to what was available in the CPU complex, because we convinced ourselves that I cannot solve this problem on the device side. It's impossible. So we started to look at the CPU complex as to how to address this problem. And we found that we really needed a standards way for the CPU complex to behave along the well-established players as well as the emergent players, so that we could do a uniform design, right? And then we started at looking at CXL 2.0 emergent concepts with respect to QoS telemetry in logical domains, but there were two problems that were not addressed as yet. The first problem was that we first look at the case of one CXL device or memory buffer that is getting sharded up or allocating to multiple VMs. And in that case, when this device is shared among multiple tenants, how do we commit a QoS SLA to the customer? That was the first problem. And the second problem was that let us assume that there are multiple devices that are connected to a single host port, right? And when there are multiple devices and for some reason one of these device slows down because it has this multi-tier memory or something like that, and it goes into a garbage collection mode or something like that, it cannot drag down all the other devices through the single port. So that was the second problem that was very challenging to us. And so we think that such concepts, we first need to address them, and then eventually continue to evolve these concepts as Dr. Wong showed very eloquently, that the devices are going to continue to evolve, and as the devices evolve with multiple different media, multiple different computational characteristics, we will need to scale up these concepts even further. The next problem that we started to deal with was the security posture for CXL memory, multi-tier memory, memory architectures. And here I bring out the chart that Alex showed, which is there is a forward-looking vision of, and I think Renu spoke about it very eloquently, of the dichotomy between storage and memory starting to converge together in a very managed way. And as we look at these forward-looking concepts where storage and memory may be operating on a single DIMM with various mechanisms, then we are starting to look at what is the security posture of this device. And without going too far in the future, but just this year, when we were looking at building devices, we came to the conclusion that we need to enable a very classical storage side, device side encryption for storage class media for all the reasons that you understand. And it just needed to be very flexible so that we could make sure that we are able to align the security bands with the VMs and so on and so forth. But the stranger problem that we started to encounter was not the device side encryption, but the host side encryption. We started to grapple with the problem that the host side encryption may actually obviate the need for device side encryption, right? Correct? Especially if you look at the latest offerings that are coming out from Azure and other cloud service providers. And then there was the other requirement of the US government and other things wanting a higher grade of security for NIST compliance and things like that. And in that case, there is additional standardization that needs to be done for the device side security to work seamlessly with host side encryption. You are very familiar with all of the key management and drive unlocking work that needs to be done for this to happen. So the security posture to me for this, Alex was trying to shine a light on how complex the security posture is for memory pooling, memory sharing, and some of these forward-looking applications, and we should not take that lightly. So in summary, you know, I think we really need to work as a group, a large collective group, so that the CXL hardware functionality can continue to evolve for rapid enablement of CXL devices, right? That's very important. And I, just based on my personal experience, page migration, CXL, DMA, QoS require an end-to-end standards-based definition so that we actually have an ecosystem that we are shepherding that can take us along a glide path. But then I feel that there'll be emerging, all of us in the media world, we are working on emerging memory technologies, and there'll be new emerging memory technology which will come out in the next 5 years to 10 years, and which will enable this multi-tier memory orchestration, computational storage, in-memory processing, and that will require new functionalities to be defined that are able to make these devices work in a robust manner at scale. And so CXL, I feel, is a journey. Really glad to get started on it, but we should keep in mind that we need to, there is a considerable amount of work that needs to be done to define these meta functionalities or additional functionalities in the upper layers of the stack, so that we can make sure that these things can be adopted at scale. That was my talk. Thank you very much for sitting through this entire session, and it has been great to meet all of you.